Welcome to this presentation on selection on observables and matching. What is selection on observables? We have heard before that randomization is a powerful tool. We use it to overcome selection problems and to estimate causal effects. So it's actually often done in practice, but when you look at it, it's done locally. What does that mean? So when you look at online advertising, and we're going to look at this in terms of an example in this presentation here, then this is often done at the level of an audience. An audience is a particular group in the population. So think of a particular age group, maybe either female or male at the same time, and at the same time in a particular neighborhood, right? Or in a particular city with a certain income. That would be an audience, and at that level, you would randomize whether somebody sees an ad or which ad that person would see. Well, think of Project STAR. So here what happened in practice was that there was randomization at the level of schools. So inside a school, within a school, people were randomized into small classes, and then the outcome, if you recall, was the test score, and the aim was to find out what the effect of being in a small class is on test scores. And the third example here are clinical trials. So here one would randomize at least sometimes at the level of age brackets, for instance. Or age gender groups would be formed, age bracket gender groups would be formed, and then you would randomize at that level. What is matching? What are matching estimators? Matching estimators have as the starting point that there are such groups. There is such a local randomization. Here I've put also the case where treatment assignment is as good as random. So in practice, sometimes one would also use these matching estimators for situations where there was no deliberate randomization, but where one can argue that a treatment status was more or less random. As for the terminology, within those groups within which treatment assignment is as good as random, one can always find good matches, right? So if one has a treated unit, one can look at the outcome, and one can always find a match of an untreated unit and basically compare the two outcomes to one another. And then one does this for many pairs of treated and controls, and one takes the average, and that's then supposedly or hopefully or under some conditions a good estimate of the average treatment effect, or the average treatment effect on the treated, or some other treatment effect parameter. And we will see in this presentation here how we should think about this and how we should formalize this. Let me jump right into this example of online advertising to fix ideas a little bit. So what you see here is a table. In this table we have two groups. We have young people, that would be group 1. We have old people, that would be group 2. And what I've put here is how many of these people there are in the population. So it would be 4 million young people and 6 million old people in the population. And that's already this number here. 40% in the population are young. 4 million divided by 4 million plus 6 million. Then I have a treated group and a control group, and I have treated individuals among the young, I have treated individuals among the old, and here you get the numbers. Okay, 6,000 treated were young, 400 treated were old. So the fraction of young people is, and then you have the control group. So here you have 2,000 in the experiment, and you have 1,600 old people in the experiment. So what that means is that in the experiment, I have 6,000 plus 2,000 among 6,000 plus 2,000 plus 400 plus 1,600 young people, and that plays out to be 80%. Okay, so 40% in the population and 80% in the experiment are young. That tells you that in this experiment they have already targeted young people. Maybe the underlying idea was that the treatment would work particularly well for young people. What is the likelihood to be treated? Then we have to, for this, we have to look at the columns here. Among the treated, we have to look at the numbers in this column here. Among the young, we have 6,000 who were treated, and the total number of young people would be 8,000. So it's 6,000 divided by 6,000 plus 2,000 is 8,000, so it's 75%. For old people, it would be 400 divided by 400 plus 1,600, so that would be 20% is the likelihood to be treated. So also here you see that among old people who did in the first place not really participate that much in the experiment, it was randomized in a way so that old people were actually more likely to be in the control group. Now, what you can do now is to look at the outcomes. These four numbers, 0.2, 0.07, 0.08, and 0.06, are four outcomes for combinations of treatment status and group membership. So 0.2 would be the average outcome among the young people who were treated. If I now look at young people, then what I can do is I can say, okay, treatment status was randomly assigned among young people, and I can therefore say that 0.2 minus 0.07 that will be the treatment effect for young people, and you see this down here. So this is the treatment effect for young people, or an estimate of the treatment effect for young people. You see this also here. And for old people, it would be 0.08 minus 0.06. So you see these numbers down here. Now, how do I now get the average treatment effect? Well, the average treatment effect answers the question, what is the effect of the treatment if I set either the whole population from not being treated to being treated, or a randomly drawn individual from the population from not being treated to being treated. So in either case, I have to use these weights here. 40% of the people are young in the population. So the chance that I'm drawing a young person is 0.4. So I have to take 0.4 times the treatment effect for young people plus 0.6 times the treatment effect for old people, and this gives us 0.064. What is that number 0.064? It is the change in the outcome, and since the outcome is a 0,1 variable, I haven't written this explicitly on the slide, but if this is the underlying idea, then these would be 6.4 percentage points. Okay, so if before they receive the treatment, the likelihood that a random person in the population, say, buys the product or visits the website is 5%, then this would increase by 6.4 percentage points. So it would be 5 plus 6.4, so it would be 11.4% when they receive the treatment. The average treatment effect on the treated is calculated in a similar way, but uses different weights. So what we now have to do is we again take these two treatment effects, but then we put the weights from this column here. So in total, we had 6,400 people who were treated. 6,000 of them were young. So that means I have to multiply the treatment effect for the young with the number 6,000 divided by 6,000 plus 400. And then I have to also add 400 divided by 6,000 plus 400 times the treatment effect for old people. And this gives together an average treatment effect on the treated of a positive change of 12.3 percentage points. So the way to think about this experiment here is really that young people were oversampled, and that the treatment effect is much bigger for young people, and that young people also were more likely to be assigned the treatment in the first place. This is also reflected in this difference between the average treatment effect on the treated, which is much higher than the average treatment effect, precisely because there were more young people among the treated. Good. So what I want to do next is a little bit dry. Please bear with me. This is mainly notation and review of concepts. I know that you have seen this before, but I find it nevertheless useful to review this at this point. So please, as I said, bear with me. So let's start with a review of conditional expectations. So let's say you have three random variables, a, b, and c, and you have two constants, f and g. Then the conditional expectation of a given c is really the expectation of random variable a if c takes on a particular value. So you can also write this down for an explicit value c naught, for instance. Okay, so when c is equal to c naught, then this is the expectation of a. So you can think of this as the subsample of observations when c is equal to c naught. Then you have surely heard of the law of total expectation before. The law of total expectation says, for the case in which c takes on a discrete value, c1 up to ck, that the overall expectation of a is a weighted average of the conditional expectation of a given that c is equal to little ck, always multiplied. So the weight is always the probability that c is equal to little ck. And finally, the expectation of constant f plus constant g times random variable a given c works out in exactly the same way as the unconditional expectation works out, namely that first of all, it's the expectation of a sum of two things. So it's the sum of the expectations. So it will be the expectation of little f, constant f, given c. That, of course, will simply be that constant, plus the expectation of g times a given c. So it will be g times the expectation of a given c. So you can always pull out a constant c. So this is exactly the same as it would be unconditionally. Next concept I'd briefly like to review is independence. So when I have two random variables a, b, and they're independent of c, and I have two constants, little f and little g, then what that means, first of all, is that a, b is also mean independent of c. Okay, so independence implies mean independence, and mean independence means this thing here. So the expectation of a given c is equal to the expectation of a. At the same time, what you see here is that you had random variables a, b together, and they are independent of c. So that does not mean that a is independent of b. And for that reason, it's also not the case that the expectation of a given b is equal to the expectation of a. So in general, they're not equal to one another. Second thing, so here I had the expectation of a given c as the starting point. Now I take the expectation of f plus g times a given c. So under mean independence or under independence, I have mean independence. So the way this plays out is that this is as before the expectation of f given c plus the expectation of g a given c. As before, this is f plus g times the expectation of a given c. And now under independence, I get also this one here substituted in. The expectation of a given c is equal to the expectation of a, so I get f plus g times the expectation of a. I know this is all very dry, so please bear with me and make sure you're aware of what these statements actually mean. So let it sink, and yeah, please bear with me. Good. So how does that all connect to the potential outcomes framework? In the first presentation where I talked about randomization, we actually had that A, B were y0, y1, and C was actually D. So independence meant that the expectation of the observed outcome among the treated is equal to the expectation of y1i, and that was quite useful. And at the same time, we had that the expectation of yi among the non-treated or the controls was equal to the expectation of y0i. So we talked about this in much detail. But then again, at the same time, please keep in mind that the expectation of y1 given y0 is not equal to the expectation of y1. Furthermore, or finally, on this slide, we can go back and forth between the potential outcomes framework and the regression framework, and one can do this in various ways. So we have seen one way in the first presentation, another way is on this slide here. So what I can do is I can say, okay, I can write down that the observed outcome is always equal to y0 plus d times y1 minus y0. So that is, that is innocuous in the sense that, you know, when d is equal to 0, then yi is equal to y0, and when d is equal to 1, then yi is equal to y0 plus y1 minus y0, so is equal to y1. So what I've written down here is simply what we have called last time in the previous presentation the observation rule, that when d is equal to 1, I observe y1, and when d is equal to 0, I observe y0. What I've done here is I've now written down that, well, one can think of this as beta 1 plus beta 2 di plus ui. And then, you know, that is also innocuous because beta 1 could be anything, beta 2 could be anything, and ui could be anything. So I've just written this out as the sum of 3 terms, right? And in some sense, this is not a big change because I can also write, this is also the sum of 3 terms when you just multiply this out. So in a way, nothing has happened. What one can then do, and this is just one way of doing it, is to say, okay, let's say beta 1 is actually the expectation of y0i. Beta 2 is the expectation of the difference between y1i and y0i. Then under independence, what we do have is that the expectation of ui given di is equal to the expectation of ui. And, you know, in some sense, what is then left over when I do all these things is that ui is going to be equal to all this business here. Okay. So what is ui? It's when di is equal to 0, it will be simply the difference between y naught I and the expectation of y naught I. And when d is equal to 0, then I'm going to have yi is beta 1 plus ui. So what I have is beta 1 is the expectation of y naught I, and ui is going to be y naught minus the expectation of y naught. So it's really, in some sense, tautological what I'm doing here. It's in the end of the day telling us what OLS, which would be based on having such an equation in our hands, in the end of the day estimates, right? So what this tells us is that the constant term that is reported by OLS can be interpreted as the average y naught I. To finish this off, so if d is equal to 1, then what I'll have is that ui is y naught minus the expectation of y naught plus y1 minus y naught minus the expectation of y1 minus y naught. So what that actually is then is y1 minus the expectation of y1i, the rest cancels. So that means I have the deviation between the actual y1 and the expected y1. And again, under independence, I have that the expected ui given di is equal to 1 is actually going to be 0 as well. So what does this tell us in the end of the day? Well, it tells us that beta 2 is our estimate of the average treatment effect here. And finally, recall that under independence, we have said that that average treatment effect is actually equal to the average treatment effect on the treated, because treatment status is randomly assigned. That was the intuition behind all that. Good. So this was independence, and this is a review of what we have done in the first presentation. Now, we bring a conditional independence into the picture. So on the previous slide, we had everything, for A, B, independent of C and constants F, G. Then we had these things holding here. So now what we do is we say, all this is still true, given X. Okay, so I still have my constants, F, G, I still have my A, B, and C. I'm just saying that A, B is independent now, given X. Okay? And what that means is I get the exact same relationships as I had before, with the one difference that there's always an X here in the conditioning set. And now it's maybe a little bit, confusing, but the point is that conditional independence is implied by independence, but not the other way around. Okay, so if I know that there is full independence, then I have more in my hands than when I know that I have only conditional independence, right? So going back to the advertising example, so full independence means that for everybody, treatment status is randomly assigned with a certain probability, and conditional independence means that this is only true actually within groups. Okay, so full independence means that group membership does actually not help me to predict whether somebody was assigned a treatment. And in some sense, in the example we had before, it was the case that it was much more likely that one got the treatment or got treated when one was young as opposed to old. So that is an example where conditional independence holds, but not full independence. Good. So let's slowly transition into more interesting territory. So all this is about formalizing a random assignment within groups, which is also called selection on observables or conditional independence. Or some people call it the CIA, conditional independence assumption, or the matching assumption. What does it do? It implies, and that is again no surprise, that the expected or average outcome among the controls in a given group X is equal to the expected Y naught given X, and the expected or average outcome among the treated in a group X is equal to Y1i given X. What that means in turn is that the average treatment effect in group Xi is given by the difference between the average observed outcome among the treated and the average observed outcome among the controls in group Xi. Okay? In that group, so for a given Xi, the average treatment effect on the treated is equal to the average treatment effect. For exactly the same reason as it was equal on the full randomization. So here we just make the argument conditional on X. So that means, expected difference between Y1 and Y naught, given that one has been treated and given that one is in group X, is equal to the expected difference between the two potential outcomes. So the DI drops out. Okay? And again, this is because of randomization. Now the average treatment effect on the treated and the average treatment effect both take weighted averages of these group-specific treatment effects, and the difference is that they put different weights. They put different weights on the groups when they take that average. In general, the treatment effect, the average treatment effect in a group is not equal to the average treatment effect in the population, because the average treatment effect in the population is averaging across groups with the population weights, basically. And therefore, it is also the case that the average treatment effect on the treated in the population is not equal to the average treatment effect in the population, and that is coming from the groups. And that comes through in the examples that we're looking at. However, keep in mind that within groups, the average treatment effect on the treated and the average treatment effect are the same, because within groups, there is full randomization. So, back to our online advertising example. So this is the exact same table as before, with the one difference that I've now put a little bit of a notation in here, simply to recap what we have just seen. So the treated RD is equal to 1, the control RD is equal to 0. I can give these two groups also names in terms of X, so I have only two groups, so I can do that with a dummy variable, so I can call them 0 and 1. So it would be a dummy for old, basically. And then I have these four averages or four expectations that I'm working with, and these would always be expected Y's, and then for different combinations of X and D. So for instance here, this would be the expected YI, the expected observed outcome, conditional on young and conditional on treated. Now, under selection on observables, under this conditional independence assumption, which is written out here, what the table above implies is that the expected treatment effect for the young is 0.13, and the expected treatment effect for the old is 0.02. And as I said, the average treatment effect on the treated and the average treatment effect are both calculated as weighted averages of these two quantities. Second example, let's go back to Project STAR and think about this for a moment. So recall that the objective was to measure the effect of assigning students to small classes. So randomization was at the school level. When we discussed that, however, we have not thought about the following two things. First, the share of students in small classes actually differed between schools. So yes, there was randomization within school, but some schools might have had many more people in small classes than other schools. And it's also likely that, not all schools have similar or comparable student populations. So it could well be that, for instance, in schools in which students were better anyway, there were more or less students in small classes. Okay, so what we have actually done in the first presentation was not taking all this into account, but simply comparing averages of between treated and untreated students, not taking into account that all these things are happening. So if we want to do it properly, this is what I'm saying here. What we have to check is whether the results actually change when we treat each school as like its own group, right? In the sense that each school has its own xi, and that we actually have to first calculate the treatment effect within each school and then average across schools after that. So that would basically give different weights to different observations, so the results may or may not change. So, xi can take on, say, two values to just look a little bit more at this example. So let's now call them xi is equal to 1 and 2 instead of 0 and 1 before. So I'm going to say, there are just two schools in the population. Then I have a treatment effect, again, an average treatment effect for school 1, average treatment effect for school 2. I have that 20% of all students are in school 1. So that means that the probability that a student is in school 1 is 0.2. And I have that 30% of all students in small classes are in school 1. Okay, so that would mean that the probability that x is equal to 1, given that a student has been treated, is 0.3, right? I can now put this into this table here. Looks a little bit like the table for advertising effects. So I have school 1, school 2. I have the average treatment effect in school 1 and school 2. And I have the probability to be in school 1, given that one has been treated, 0.3. It means that, since they have to sum to 1, it's 0.7 for the other school, and the probability to be in school 1 unconditionally is 0.2. Okay? So I have 0.2, 0.8, and 1. What are the weights for the calculation of the average treatment effect on the treated? Well, then I have to take these weights. Okay, so I take 0.3 times this plus 0.7 times that. And for the calculation of the average treatment effect, there will be 0.2 and 0.8, and otherwise I do the same calculation. Good. So I've now talked a lot about selection on observables and conditional independence. And again, this can be written down like this. So given X, given group membership, the two potential outcomes are independent of D. So I have randomization given X. There's actually a second condition that is important in this context, and that is called a common support or overlapping support, what does support mean? Support is the set of values a random variable can take on. Okay. And here what it means is that for a given x, given that I is in a particular group, the probability that I is actually treated is not 0 and is not 1. And that means that there are treated and untreated units in each group. If this would not be the case, then we would be in trouble, because then we could not estimate the treatment effect at the group level before then averaging across groups. Good. So let's now think more about this whole matching idea. So suppose we want to estimate the average treatment effect on the treated. Okay, so our object of interest is the expectation of y1i minus y0i given di is equal to 1. What is now that matching idea? That matching idea is that for each unit I in the treatment group, so let's denote this by I is in T, T means treated, the set of treated individuals. What we can do is we can construct a counterfactual outcome from the outcomes we observe for other units J in the control group, denoted by J is in C, in the following way. We calculate a weighted average of the outcomes of units in the control group where the weights, where there are some weights, Wij, are specific to that combination of I and J. Okay? And they would sum up to 1 when we sum over J. So that means if I take the starting point unit I and I look at all theWij's and I sum over J in the control group, then these weights would sum up to 1, and again I is in the treatment group. Okay, so I take a unit I is treated, I look at all people who have not been treated, and then I assign basically weights to all these people to say which ones contribute how much in terms of that weight when I calculate a counterfactual outcome for that unit I. So what do I need to do for that? I need to say, okay, the weight should be higher. The weight Wij should be the higher, the more similar I and J are in terms of observed characteristics xi and xj. Okay, and there are various ways in which one can do that. Let's keep that abstract for the moment. Then for unit I, ultimately the estimated treatment effect is going to be the outcome for unit I. Again, I has been treated, minus some constructed average outcome for control units. So I have here these weights. So I'm starting from I. So I'm going to have weights Wij, and I'm taking the average over units J, right? And here I have the outcome Yj of these control units. So that means for each I have an estimated treatment effect. I have this basically stored in my data. That's step 1. And step 2 is to estimate ATT. What we need to do is we have to average over I's, right? So first step, we construct a counterfactual for each I, and we subtract that from the outcome of unit I. Second step is we average over treated units I. And for this, we assign another weight to unit I, so that would be Wi, and usually we just give equal weight to each I. So that would be Here I've written this as WIATT for the average treatment effect on the treated. That would simply be 1 over N1, where N1 is the number of treated units. Okay, and using this we can write the estimator as I'm averaging over treated units with the weights WIATT of the individual level estimate of the treatment effect. So it's YI minus that constructed counterfactual outcome if they would not have been treated. That is all for the average treatment effect on the treated, and that's really that whole matching idea that is always floating around here. Finally, to estimate the average treatment effect, we do pretty much the same thing. The one thing that is different is later this weight. So instead of the WIATT, what we're going to do is we're going to use a weight WIATE, which is not 1 over N1. So it's not equal weight to all the treated units. No, it is proportional to 1 divided by the probability that unit I has been treated. Okay, so what that means is that I'm actually going to give more weight to units that were less likely to be treated in the first place. So it is more special that we see them treated, and therefore we want to overweight them, and we give them more weight, and others who are very likely to be treated will receive less weight. And this is called inverse probability weighting. To illustrate this a little bit, what we see here is an example with 3 units, unit 1, 2, and 3. Here I have the 3 estimates of the treatment effects at the level of these units. So again, these are treated units, so they have an outcome Y1I, and I subtract from this the constructed Y not I hat, and then I end up with estimates of the individual treatment effect of 10, 20, and 30. And for the average treatment effect on the treated, I said that I would use equal weights for these estimated treatment effects. So it's just really the average between 10, 20, and 30 that I'm taking here. And of course, that will be 20, as we see here below. I said before that for the average treatment effect on the average treatment effect, in contrast, we would like to take into account how likely it was that a unit would be treated, and that I would like to give more weight to units that were less likely to be treated in the first place. And I would do that by picking weights that are proportional to the inverse of the probability that a unit has been treated given its characteristics. So for 0.5, I would then have a weight that is 1 over 0.5, and then here in the denominator I simply sum up over all the weights I get in that way. So 1 over 0.5 plus 1 over 0.4 plus 1 over 0.2, because 1 over 0.4 would be in the numerator for the second I, and 1 over 0.2 would be in the numerator for the third I. So these weights do all sum up to 1, and if I use them, then what I get is an estimate of the average treatment effect of 23.16. Now, I said before that there are different ways to construct these weights, Wij, that I used to estimate counterfactual outcomes. So now I want to provide a bit more detail about this. So first of all, there's something that's called exact matching. Then a second way can be described as matching based on the closeness of observables. And here we have three types: nearest neighbor matching, k-nearest neighbor matching, and kernel matching. And finally, there's something called propensity score matching, which reduces the dimensionality and has certain advantages. Good, let's start with exact matching. So exact matching means when I have that treated unit I want to look for a control unit that has the exact same x j equal to xi. Okay, so this is basically what I always talked about in these earlier examples for Project STAR. So this would be a unit in the exact same school, or in this advertising example, it would be a unit in the exact same group. And then when one does that, when one has all these units xj that have the same, all these units j that have the same xj as xi, one can simply count how many one has, say nx, and then one would just give equal weight to all of them and take the average of the outcome for all these control units that have the same x. And otherwise, one assigns a weight of 0. So again, the example is the counterfactual is the average test score for students in the control group in a large class at the same school. Now, the thing here is that we can only estimate counterfactuals for observations with characteristics xi if there are actually observations in the control group with the exact same characteristics xj is equal to xi. And that is possible and often likely if all the variables in xi are discrete and if one does not have too many of them. Okay. So ideally, the control group has many observations at each distinct value of xi. If that's not the case, then you can still pursue the same idea, but then in a slightli more general way. So what one would do then is that for each participant I in the treatment group with characteristics xi, we would compute a counterfactual outcome, which is based on outcomes for observations in the control group with similar characteristics. So xj is then not equal to xi anymore, but it's approximately equal to xi. You can think about it in that way. So one version of that is k nearest neighbor matching. So first of all, you need a measure for the similarity. So you can simply take the norm, the L2 norm. That would be, you take the difference between xi and xj. So think of xi really as a vector, right? And xj as a vector, you take the difference, that gives a vector, and then you just square all the elements and you add them up, these squared elements of that vector with the difference between the two vectors. So that gives you a measure of the distance between xi and xj, and obviously when they're exactly the same, that measure is equal to 0, which is the minimum, right? And then the k nearest neighbor matching approach would assign a weight of 1 over k, wij is 1 over k to the k most similar control units according to that measure. And nearest neighbor matching basically uses k is equal to 1. right? And if there are 2 units that are similarly exactly as far away from xi as one another, then one basically does take the average between those 2 units. The next thing that is similar is kernel matching. So what one would do here is one would basically again use that norm. So one measures the distance between xi and xj, and k is simply a weighting function. Okay, around that. If that distance is 0, then that k evaluated at 0 would be biggest, and the bigger the distance is, the smaller the weight would be. And what you see here is really the weight of observation j for observation I is k evaluated at the distance between the 2 x's, and here in the denominator you simply see all the weights for all the observations in the control group added up, so that the wij's will sum up to 1. And this is also explained here. What one needs to do is one needs to choose a functional form and a bandwidth for that so-called kernel function k, but it turns out actually that in practice that this will not matter all that much, but you need to make some choices. Now a little bit more guidance. So matching only based on the nearest neighbor has less bias. So there's a bias variance trade-off here, so it has less bias since the difference in observed characteristics is minimal. However, matching on more neighbors has less variance. Okay, because each counterfactual is calculated as the average of more observations, intuitively speaking. So you have to make a call here. What you think works best, and obviously there are ways of systematically finding out which parameter values for these choices are the best ones. Think of some cross-validation procedure. Finally, propensity score matching is an attractive route when one has high-dimensional X's. So let's see what propensity score matching looks like. So first of all, what is the propensity score? The propensity score is simply the probability that a unit is treated given x, and we can write this as a function p of x I. Then there's an important result. This is all based on, and this is by Rosenbaum and Rubin. And what they have shown is that when y naught is independent of d given x, then it will be the case that y naught will also be independent of d given p of x. Okay. In principle, you can broaden this and you can say, y naught y1 is independent of d given x, and y naught y1 is independent of d given p of x. But we don't even need that here because we're only constructing a counterfactual outcome for a given treated unit. What that means is that we don't need to form the groups on the basis of x. It's enough to form the groups on the basis of the likelihood that a member of a group is being treated. Okay, so in practical terms, so if I have 3 schools in Project Star, and I know that the likelihood to end up in a small class is, say, 0.4 in the first school and 0.6 in the second and 0.6 in the third, then what I can actually do is I can pool the data from the second and the third school together, because the second and the third school, they will have a different x, but they will have the same p of x. Okay, so this is what a propensity score matching relies on. Basically, you don't need to look at all the fine details in all the x's. All that matters is differences between groups in the likelihood of being treated. So what this means technically is that we can match based on the one-dimensional p of x instead of the higher dimensional x, because the expected y naught I given di is equal to 1 and p of x is equal to the expected y naught I given di is equal to 0 and p of x, and that is equal to the expected observed outcome, or the average observed outcome among the controls that have the same propensity score as treated unit I. Right? So what that means, again, in terms of that whole matching procedure, is I have a unit I know that for that unit I it is in a particular group, and that particular group has a treatment probability of 0.4. So what I then need to do is I need to find control units in other groups or in the same group that have also a treatment probability of 0.4. So in a way, you can think of this p of x also as just an x. So that means that all matching algorithms stated above can be based on p of x instead of x. Potential advantage is that you can find better matches, because it could be that p of xi is similar to p of xj, while xi is very different from xj. Potential disadvantage is that you have to estimate the propensity score in a first step. So for instance, with a logit or a probit model, and this may lead to bias. But I would say that in many cases, the advantages are more important than the disadvantages. So we're already nearing the end of this presentation. I have not yet talked about OLS really as a matching estimator. We have talked about this idea before, that you can simply regress the outcome on a treatment indicator once random assignment holds. So when random assignment holds for given x, one might have the idea that one simply controls in addition for x. So an x would here indeed be a vector, right? So xi and gamma are both vectors of the same dimension, so therefore this is a scalar because it's the inner product of these two vectors. So yeah, one could just do that, right? So first of all, this assumes linearity in xi. That is not a problem per se, especially not if all covariates are discrete. Then we can put into xi lots of terms, so we can actually estimate a fully interacted model. We can also discretize the elements of xi and use polynomials, etc. However, it's actually unclear which parameter is estimated when we do that, right? And in particular, which parameter is estimated if the effect of d, which here is this beta 2, also depends on x, right? Because we haven't really captured this in this model here. And in general, we will neither estimate the ATE nor the ATT, but some other weighted average of treatment effects. So I would say it's not completely unnatural to do this, but one should be aware of the fact that one is not estimating the ATE and one is not estimating the ATT in general. One will if, for instance, the treatment effect is the same for everybody, but normally one does not know that. What one could do instead is to do something that is called flexible OLS estimation. So that's a very similar approach, but there's a difference. And the difference is that one actually includes a term that then captures the dependence between the effect of D on Y and on X, basically, right? So here what we have is that xi minus x bar is a vector of demeaned covariates that is then interacted with di. So one includes as additional regressors. So when you have 15 x's, right, you would include 15 extra terms, and these would be interactions between the demeaned x's, demeaned across all observations, and di. Okay. And delta here then is the dependence of the treatment effect on x. Now, let's inspect this a little bit more. So when xi is equal to x bar, which is the case for the average individual, already hints at the average treatment effect, then the expected difference in the outcome will not depend on this part here, because xi is equal to x bar. So the expected difference in the outcome is beta 2. Okay. So what that means is that you run this regression here, and then under conditional independence, when you have used this specification here, then beta 2 will be directly your estimate of the average treatment effect. If you then say, yeah, that's nice, but actually I'm interested in the average treatment effect on the treated, then what you can do is you can go back to this equation here, and you can say, okay, good. For the treated, what I have is that the effect is going to be beta 2 plus basically the difference between the average x for the treated and the average x in the population times delta. And this is exactly the case that you have to use this in order to calculate the average treatment effect on the treated. So again, you take your estimate of the beta 2 and your estimate of the delta, and you add to the estimate of beta 2 the average, and here it's the average among the treated units of this quantity here. Okay, so for the treated units, this is going to be, so this D is simply picking the treated units. Here I'm summing up overall, so this is actually the average of the treated units of xi minus x bar, and then I multiply this by delta hat. So it's relatively easy to use actually a regression to estimate the average treatment effect and the average treatment effect on the treated, if one feels comfortable making the assumption that this is approximately correct specification, or formally that this is the correct specification, in the sense that linearity in X is not too bad an assumption. And again, what you need to do there is you need to put enough terms into this Xi vector, enough interaction terms, higher order terms, or you can discretize to make that a good approximation. Finally, let's end with the key concepts that we have learned about. First of all, it's all about conditional independence or selection on observables, which essentially means that we have randomization at the level of groups, and group membership is observed. Then we can use various estimators that in the end of the day all do the same thing. So you have say proper matching estimators, and here we have seen very briefly what exact matching means. We have seen what matching on closeness of observables means. We have seen what propensity score matching means, and why it might be a good idea to use that. And the last thing we've seen is that our good old OLS estimator turns out to also be useful here in this context. And when we use this specification with the interaction between di and xi minus x bar, then we can estimate directly the average treatment effect, and we can then calculate relatively easily the average treatment effect on the treated without much of a fuzz. And that's, I think, a great note to end on. So yeah, with this, I hope this was useful for you. All the best.